Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the intellectual crucible of the early 18th century, a period still incandescent from the analytical firestorm ignited by Newton and Leibniz, the calculus was less a settled continent of thought and more an archipelago of powerful techniques awaiting systematic exploration. Into this vibrant and fiercely competitive world stepped the Scottish mathematician James Stirling, a figure whose personal life, marked by Jacobite sympathies and continental exile, was as complex as the infinite series he sought to tame. His magnum opus, the 1730 publication titled Methodus Differentialis Sive Tractatus de Summation et Interpolation Serierum Infinitarum, stands as a towering monument in the landscape of early modern mathematics. It is a work of profound practical ingenuity and theoretical foresight, a critical nexus between the foundational calculus of the 17th century and the towering analytical structures that would be erected by Euler and his successors. The Methodus Differentialis reveals itself upon close inspection as far more than a collection of computational recipes. It is a systematic treatise on the behavior of functions at infinity, a masterclass in the art of approximation, a source of one of mathematics' most ubiquitous and elegant form. The genesis of Stirling's work lies in the central mathematical challenges of his era. With the power of Taylor and Maclaurin series expansions freshly established, mathematicians possessed a tool for representing functions as infinite polynomials. The immediate and pressing problems became how to manage these infinite objects. How could one find the sum of a series that converged with agonizing slowness? How could one estimate the value of a function or its integral where direct computation was impossible? These were questions of immense practical import, driving developments in fields as diverse as celestial mechanics, where planetary orbits were computed via series, and the burgeoning science of actuarial tables, which depended on the summation of terms related to annuities and life expectancy. The intellectual antecedents to Stirling's project are clear. He was building directly upon the edifice of Isaac Newton's method of fluxions and his work on finite differences, particularly the Newton interpolation formula. A more immediate and personal influence, and indeed a rival, was Abraham de Moivre. De Moivre's investigations into probability, chronicled in his De Mentura Sortes and the later The Doctrine of Chances, constantly led him to confront the challenge of approximating sums with a vast number of terms, most famously in his work on the binomial distribution. Stirling's Methodus Differentialis can be viewed as a direct, and in many respects superior, response to the very problems that occupied de Moivre. Striving for greater generality and computational efficiency, the treatise itself is a work of meticulous structure and clarity, divided into two principal parts that address the twin problems of summation and interpolation. The first part introduces a suite of powerful techniques for accelerating the convergence of infinite series. Stirling's primary method, a transformation that now bears his name, is a marvel of analytical insight. He recognized that many slowly converging series could be converted into new series, whose terms diminished with far greater rapidity, by systematically employing the calculus of finite differences. Conceptually, for a given series defined by its terms a sub I, Stirling constructed a new, related series whose terms were built from the forward differences of the original sequence, delta a sub I, delta squared a sub I, and so forth. This procedure effectively filtered out the slow, polynomial-like behavior of the original series, leaving a residual part that converged much faster. He presented a variety of such transformations, each tailored for different classes of series, providing the 18th century mathematician with a formidable toolkit for numerical computation. This was an act of profound algorithmic creativity, enabling calculations that were previously intractable and pushing the boundaries of what was computationally possible. With pen and the second part of the Methodus Differentialis deepens the theory of interpolation, the art of reading between the lines of a table of data. While Newton had laid the groundwork with his forward and backward difference formulas, Stirling's contribution was both a refinement and a powerful synthesis. He introduced the central difference interpolation formula, today known as the Newton-Stirling formula, which possesses superior accuracy for interpolating values near the centre of a known range. He artfully constructed this by taking the arithmetic mean of Newton's forward and backward formulas, a seemingly simple step that yielded a more symmetric and often more stable result. This was a quintessential example of Stirling's style taking an existing powerful idea and honing it into an instrument of greater precision and elegance. His treatment extended beyond mere polynomial interpolation to the more complex problem of quadrature, or numerical integration, providing methods to approximate the area under a curve by evaluating the function at a discrete set of points. Within this treasure trove of analytical techniques lies the book's most celebrated legacy, a result so fundamental that it is known to virtually every student of science and engineering. Stirling's approximation for the factorial function. The problem arose, once again, from the work of de Moivre, who, in his quest to approximate the central term of a binomial expansion for large exponents, had derived an expression for n factorial. De Moivre's formula was correct in its functional form but was missing a crucial numerical constant. Stirling, driven by the desire to find a continuous function that could smoothly interpolate the discrete values of the factorial, embarked on an analytical journey of his own. The result he published in the Methodus Differentialis was breathtaking. He demonstrated that for large values of n, the quantity n factorial is asymptotically equivalent to the expression the square root of the quantity 2 times pi times n, all multiplied by the quantity n divided by the mathematical constant e, with this entire second part raised to the power of n. Stirling's signal achievement was the rigorous determination of that mysterious initial factor, the square root of 2 pi. He accomplished this through a brilliant and non-obvious application of the Wallis product for pi, linking his problem of discrete summation to a classic result from the integral calculus. It was a moment of supreme mathematical connection, a testament to his deep intuition for the hidden relationships that bind disparate areas of analysis. One can almost picture the quiet satisfaction he must have felt in supplying the missing piece to de Moivre's puzzle, a subtle but decisive intellectual victory. Beyond this famous result, the book also implicitly introduced the combinatorial objects now called Stirling numbers of the first and second kind, which arise organically from the process of converting between powers of a variable x and the falling factorial powers used in finite difference calculus. The reception of the Methodus Differentialis among the European mathematical elite was immediate and positive. Its methods were too powerful to ignore. The great Leonhard Euler, a voracious consumer and producer of new mathematics, seized upon Stirling's techniques with enthusiasm. Euler's own work, particularly the development of the celebrated Euler-Maclaurin formula, can be seen as a direct intellectual descendant of Stirling's project. The Euler-Maclaurin formula provides a more general and profound connection between a sum and its corresponding integral, but it addresses the very same class of problems that Stirling tackled and undoubtedly drew inspiration from his methods of relating sums to derivatives and differences. The book's influence, however, extends far beyond the specialized world of 18th century analysis. Stirling's approximation for n factorial became an indispensable tool in the development of statistical mechanics in the 19th century. Physicists like Maxwell and Boltzmann, when analyzing the statistical behavior of gases containing astronomical numbers of particles, needed to evaluate factorials of these immense numbers. Direct computation was an absurdity. Stirling's formula provided the key, allowing for the derivation of fundamental results like the Maxwell-Boltzmann distribution of molecular speeds, a cornerstone of thermodynamics. The legacy of the work also permeates the modern field of numerical analysis. The core ideas of series, acceleration, interpolation using differences, and numerical quadrature are now foundational algorithms taught to every science and engineering undergraduate. While today's methods are often more sophisticated and are implemented on digital computers, the conceptual DNA can be traced directly back to the pages of the Methodus Differentialis. Of course, it is essential to view Stirling's work through the lens of its time. The analytical methods of the early 18th century operated with a spirit of bold, formal manipulation, possessing a level of rigor that would make a modern analyst uneasy. The convergence of the series being manipulated was often assumed, and the interchange of limiting operations was performed with an intuitive confidence that preceded the strict epsilon-delta definitions of Cauchy and Weierstrass. By nearly a century, this absence of modern rigor is a feature of the era, an indicator of a field driven by the pursuit of powerful results over axiomatic purity. The Methodus Differentialis is an edifice of breathtaking computational power built upon foundations of inspired intuition, a structure whose full and formal justification would wait the coming century of analysis. In conclusion, James Stirling's Methodus Differentialis is a masterpiece of classical analysis, a work that perfectly encapsulates the mathematical spirit of its age while casting a long shadow into the future. It is a practical handbook of immense power, a theoretical treatise of subtle depth, and a personal statement of intellectual prowess from a mathematician whose name deserves to be uttered in the same breath as his more famous contemporaries. Stirling was a supreme craftsman of the calculus, a master of the art of approximation who provided his peers and his descendants with tools to solve problems of immediate physical and commercial importance. Through his brilliant transformations of series, his elegant refinements of interpolation, and his immortal approximation for the factorial function, he fundamentally advanced humanity's ability to understand and compute the behavior of complex systems. The Methodus Differentialis is more than a dusty historical artifact. It is a living document whose ideas are woven into the very fabric of modern scientific computation, a lasting testament to a remarkable mind navigating the fertile and uncharted waters of the infinite.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.